Okay, it's time to start. So I'll go over the record real quick. I don't see Amanda or Chad. Reagan stepped out. Diksha. Austin's here now. Jaron and James. And Reagan's back, just because I said his name. Okay, so we're good with that. Hopefully the lab final, or lab whatever, practical, didn't stress you. It should have been mostly things that you've been doing every week for 3 months. So hopefully, I haven't graded them, but I'm hoping it was positive impact on your grade. Okay, start off with the clicker question related to the last lecture. Which kind of energy is proportional to the temperature in an ideal gas? Okay. We had similar to what we had answers last class period. I had hoped after explaining it we would have uniform agreement, but it's been a couple days. We went through last class period the derivation of the kinetic theory of gases. The reason we went through that derivation was so you can see that there's actually a sequential set of steps that are not that difficult, things you already understand, that tie the translational kinetic energy to temperature. And so we learned that the average translational kinetic energy was equal to, what was it? 3/2, 2/3? I don't remember what the fraction is. Yeah, I think it was 3/2 kT. And so that's what we're told, that's what temperature tells us if it's an ideal gas. If it's not an ideal gas, of course, the relationship between temperature and translational kinetic energy is going to be different. And our textbook actually doesn't talk about the other kinds of energy, and I'm not going to introduce them right now at the very least because we've got more important things to do right now. So let's look at those more important things. We also looked at these graphs last class period. These are graphs of the actual distributions of speeds you'll have in a gas. They're not all the same speed because you're having collisions. And when you have collisions, you're going to have, depending on the collision, some things might speed up and some things might slow down. But when you increase the temperature, you should have faster speed since temperature is telling you about the average kinetic energy. And so in these two graphs, we can see the higher temperature corresponds to higher speeds. And one of the things you did in Flip Friday was look at this and say, this is the most probable speed right here because you are at the peak of probability. Kind of like if you were to roll dice, if you roll 2 dice, what's the most probable outcome of rolling 2 dice? It's going to be 7. That doesn't mean when you roll it, you're going to get 7, right? You get lots of different values. So that's the same thing we have with these molecules. They don't all have the most probable value, but that's the one that's most likely. And then we can look at this and say, well, the probability of being above that most probable is bigger than the probability of being below it just by looking at the area. The area on this side is actually a fair amount bigger than the area on the other side. And so that means you have a bigger probability of being on the faster side of the most probable. You're going to have a higher than average velocity. than your most probable velocity. And for people in the Physics 251 class, we worked out the mathematical relationships yesterday between the most probable velocity, the RMS velocity, and the average velocity. If you have this distribution, they're all related. I keep doing that. Go forward on the wrong thing. Well, it's the second time I've done that. Looking at ways we describe a thermodynamic system. We like to view things. One of the questions you had on the lab test yesterday was, why do we make all these graphs? A primary reason to make the graph is because we can look at the graph and quickly analyze what's going on, pick up information. So when I look at these graphs, these have pressure on the vertical axis, volume on the horizontal axis. Now, these are not the most commonly viewed graphs, but they're useful graphs for telling us about things like what's going to happen when you change phase. Now, I'm going to have for your Flip Friday working on heating, both what happens when you're heating something without changing phase and what happens when you heat it and change phase. But if we look at these graphs, we can see what's happening. If we have temperature 1 that's fairly low, on this side of the blue, it says vapor. Vapor, gas, same thing. So this is gas over here. Over here it's liquid. And what do you suppose that blue thing is going to have to be? It says on the other graph, I know. It is the combination of both liquid and vapor together. So we can look on this graph, these are constant temperature, so the temperature is staying the same everywhere. And to change the volume and pressure, well, pressure and volume are related to temperature, PV equals nRT, if it's an ideal gas. Is it behaving like an ideal gas if you have a liquid? One person gave an answer. I hope more people. Is it behaving like an ideal gas if it's a liquid? No. Because it's a liquid, not a gas. And even when you're close to this region, it's still not going to behave like an ideal gas. You can look over here, and everything in this region is not behaving like an ideal gas. An ideal gas, P is equal to 1 over V times nRT. And so this should have a 1 over V relationship. They should be nice smooth curves that look like this or this, not having any wiggles on them. Right? If you graph 1 over X, that's what a 1 over X curve looks like. So if it's behaving like an ideal gas, it should look like that. So I can look and say all these things that I circled are not behaving like an ideal gas. Why are they not behaving like an ideal gas? They're what?
They're not ideal gases.
Okay, well, they're not ideal gas. Nothing is truly an ideal gas, but a lot of things behave like them. But what condition do I need for a gas to behave like an ideal gas? Need what? Okay. High temperature, low density. Well, in this case here, the temperature isn't high enough apparently. If we were to go out in greater and greater volume, we'd be going to lower and lower density, and it would be behaving more and more ideal even at that temperature. Okay, so these are somewhat useful. Notice up here at the top we have the critical point. The critical point is the highest point where we can have a separation between a liquid and a gas. If you're beyond the critical point, that is if your temperature is above that critical temperature, or, well, this here, right, that says TC there for critical temperature, then you don't have a distinction between a liquid and a gas. That seems really odd to us. We're really used to having water, having steam. I can have my hand in air, a gas, hit water, splash, right? It goes from one to the other. But if you are above this critical temperature, you can never have that. You can just have thicker and thicker gas until you get to the point where you say, you know, this really isn't a gas, this is a liquid. And so that's the key about that critical temperature. If you are above the critical temperature, there is no distinction between liquid and gas. It's just thicker and thicker and thicker, or thinner, thinner, thinner. Now looking at the graph you're more used to seeing, called a phase diagram or a pressure temperature diagram. I assume you're more used to seeing this. I know in physics we're more used to seeing this. Question, Ryan?
Just real quick, with that critical point and region, what do we call that phase? Did I miss that?
There's not a specific name for it as far as I know.
Okay.
It's a fluid.
It's kind of a bizarre.
Fluid, something that flows, but you can't distinguish between a liquid and a gas. And some people use vapor to mean one thing, some people use gas. There's not a good, strong term. Here are phase diagrams. We call them phase diagrams because they're a lot easier to identify phases with than the pressure volume graph. So on this pressure temperature graph, you have the temperature. Notice it's increasing to the right. It's not a linear scale. It's a logarithmic scale in this graph. It could be linear, it could be logarithmic. It depends on who makes the graph and what they're trying to show. Vertical scale is once again logarithmic. And you have the critical point on this graph as well. The idea of the liquid, the gas, and so on. I'm sure I'm blocking somebody's view. Since Jaron's not here, I'm not blocking anyone's view here. The idea of the critical point and the phases. This right here, it says L for liquid. That's a liquid phase. Anything below this dashed line at 218 atmospheres and between those reddish lines is going to be a liquid. This down here says V for vapor. Anything that is to the left or lower temperature of 374 degrees Celsius is going to be a vapor or gas. What do we call the stuff out here was the question that Ryan was asking. Right? It doesn't have a fixed name to differentiate it. We can say for sure this vapor, or if you prefer, which I do, gas, we can say here it's definitely a vapor or gas. We can say here it's definitely liquid, but if it's out here, I can't say. But what we can do is we can do an experiment where we could take some water that is right here at 1 atmosphere and a temperature of, let's say, 70 degrees Celsius. Water at 1 atmosphere, 7 degrees Celsius, that's a liquid. We could then take it and increase the pressure to get the pressure up to, let's say, 300 atmospheres. And then at 300 atmospheres, we could heat it up to around 500 degrees Celsius, then lower the pressure back down to atmospheric pressure, and finally lower the temperature down to about 110 degrees Celsius. At 110 degrees Celsius, water is a vapor. We call it steam. And so we would have something we would readily identify as steam here. Here we had something we readily identified as water. But going on this path, we never crossed this reddish line. I don't know what to call that color. Rust? I don't know. We never crossed that line. That line is where it changes phase from a liquid to a gas. We never crossed it, never changed phase. And yet it went from what was clearly identifiable as liquid water to what is clearly identifiable as steam. The process simply, it became less and less dense as we went through that cycle. Actually, we started by increasing the pressure. It became more dense as we increased the pressure, then less dense as we heated up and lowered the pressure. But it never changed phase. That's a very interesting thing that occurs because there's that critical point above which you can't have a distinction between a gas and a liquid. The triple point is another important point. The triple point we've talked about, it's where you can have all three of our common phases, gas, liquid, and vapor, coexist. It's a very specific temperature and pressure. So it's marked here as a single point. That's why we use that these days for our reference point for calibration of the Celsius scale, because it's very specific. What do we have on this side? It says S, that stands for solid. I'll put it downward. S-O-L-I. My I and my L look a lot alike, but it's solid. So this line here is separating what two phases? It's separating a solid and a gas. If you go from a solid to a gas, it's called sublimation. If you go from a gas to a solid, I forgot to look up the word for it. There is a word for going from gas to solid. I didn't look it up. If you go across, I'll change colors here. If you go across this line that I'm now coloring in green, let's say you go from the left side to the right side of that, what's going on? It's melting. If you go from the right side to the left side, it's freezing. Thank you. Like, wow, I know everybody knows that going from liquid to solid is freezing. And then finally, we have the one that I've been working around. This line here, if you go from left to right across that line, what's it doing? From your left to your right, which is my left to my right if I look at this. Okay. Anybody else with Tori on this? What's it doing if you go across this line going like this? Really? Okay. It's evaporating. It's vaporizing. That's the same root word there. It's going from the liquid to the gas phase, evaporating. What do we call it if it goes the other direction? Condensation. It's condensing. Okay, so we have these words that describe the changes that are easy to see on the phase diagram, hence the name phase diagram. Now this one here is water, as is readily visible. This one here is carbon dioxide. What do you notice that is clearly different about these two graphs? The biggest difference is the curvature of the green line, the one between solid and liquid. This is the more normal curvature. What that means is if I stay at a constant pressure and constant temperature and increase the pressure, the carbon dioxide, when you increase the pressure, you're going to be moving up, and it would move from liquid to solid. Over here, if we look at water, let me draw some magenta lines to illustrate my point. With the CO2, if you keep it constant temperature and increase the pressure, it's going to go from the liquid phase here to the solid phase there. But the water, it would go from the solid phase here to the liquid phase. So water, when it's at pressures close to atmospheric pressure, if you increase the pressure, you're likely to melt it. That's unique and different. And you've probably heard a lot of talk about things like ice skating. Ice skating, when you're skating on your ice skates, you are creating a water layer and skating on the water. So that's much lower friction. Now there's a lot of people who studied this, looked into it. Is it because the blade is warmer than the freezing temperature of ice and it's melting because it's warmer? Or is it because you're putting pressure on and melting with the pressure? And I believe the conclusion is because you're putting pressure, it's melting with the pressure. Now, if you get too cold, you notice that, well, you get down to a temperature here, and no matter what pressure you put on, it's not going to melt. So you get too cold and you can't melt by adding pressure to it. And so at that point, well, the ice skate would be sticky because it's not going to melt the ice. Water does eventually curve back like this. Water has lots more phases than just the standard 3. There are at least 7 different phases of ice for water. And so what makes it a different phase? It's actually a different structure of how the atoms are, or the molecules are aligned, that gives it these different phases. And so, if you continue this thing on, it goes something like, oh, wait, not in drawing mode. It goes something like this up there. We're not worried about that specific behavior. Carbon dioxide, notice where 1 atmosphere is. 1 atmosphere is right here. What phases can you have with carbon dioxide at 1 atmosphere? Only a solid and a vapor. Hence, we call frozen carbon dioxide dry ice. Dry because it doesn't melt. You can't have liquid carbon dioxide at atmospheric pressure. You have to get up to 5.11 atmospheres before it's possible to have liquid carbon dioxide. So that's what dry ice is. It's just frozen carbon dioxide. All right, I'm going to move forward from here. I've already spent way more time on the phase diagrams than I intended to. I do have our second clicker question finally. Which transition is impossible? Or okay. 1, 5, 12. Move from solid to gas without going through a liquid phase. I just finished talking about dry ice. Dry ice at atmospheric pressure doesn't have a liquid phase. It goes directly from solid to gas. What do we call that process of going from solid to gas? Sublimation. Okay, so that was not the correct answer. That's certainly possible. The next one, move from liquid to gas without having a phase transition. That's what I drew that pretty little diagram for with water. If you go around the critical point, you can go from a liquid to a gas without ever having it vaporize. You have to cross that phase line for it to go through evaporation. So that one was not correct, leaving us with move from solid to liquid without going through a phase transition. On those phase diagrams, going back to the phase diagram here so we can see it, there is always a line here between the solid and liquid. That line will never end. So it can't go around and miss that transition. So that's the one that was not possible. Okay, speaking briefly about boiling. What do you think happens when water boils? Hey, what? Okay, you have to add energy to water usually to make it boil. but what's happening in the water itself? Okay? Molecules are moving faster. If they move faster, they can then do what? They can break away from the surface. Now, it turns out that you are constantly having water molecules that leave the surface. So if I have a cup of water sitting out here, I'm going to have the amount of water in that cup drops almost always. Because we learned about the Maxwell-Boltzmann distribution, that distribution of speeds. Well, let's just draw a line, kind of randomly drawn. Let's say this here is the speed that the water molecule has to have to break away from the surface, right? Think of it like a BB. You know, if the BB goes fast enough, it can break through a piece of paper. Same idea with the water molecule. If the water molecule goes fast enough, it can break through the surface barrier. So there's just a speed that's associated with the water molecules leaving. In a distribution that follows this Maxwell-Boltzmann distribution, are there ever any molecules with speeds higher than that speed? There always are. So you're always going to have some molecules that are leaving the water. You're always going to have some amount of evaporation. And so that puts water into the air. But of course, if there's water in the air, the water molecules in the air will be moving around. Some of them will hit the water surface and go back in. So if you put a cup of water out and you leave it out for a couple days, a lot of the water that's in the cup a couple days later wasn't in the cup when you started. Because you had water that evaporated out, water that came from the air and went into the cup. Which kind of helps explain why the water tastes kind of gross if it's just been sitting out for a couple days. So we constantly have this process. Now there was the idea of relative humidity that you learned about last Friday. Relative humidity is what we usually mean when we say humidity. Humidity is the amount of moisture in the air. Relative humidity is the ratio of the moisture in the air to the total amount of moisture the air can hold. And hot air can hold a lot more moisture than cold air. Hence, if you have the temperature suddenly drop and keep the same amount of moisture in the air, you can go from no problem to more moisture in the air than it can hold. That would be a relative humidity that's more than 100%. Well, what happens if there's more moisture in the air than it can hold? It falls out. Rain, right? So rain occurs, it's actually in the clouds where you have that supersaturated situation, more moisture than the air can hold, and so then you form droplets that fall out. Here on the surface of the earth, it doesn't have to be 100% humidity to rain, because the water droplets weren't forming here, they're forming up in the clouds. But in the clouds, 100% humidity. If you're walking around and there's a fog, you're pretty much in a 100% humidity situation because that fog is little water droplets that formed out of the air. That helps explain things like, you know, when I go to the gym, I didn't this morning, but normally I would have gone this morning. When I go to the gym after working out, I get in the car, close the doors, and instantly my windshield gets fogged over. Why would my windshield get fogged over? Okay, what was it? The air got, what I heard was the air got dropped.
No, trapped.
Trapped. Is that what you said?
Yeah.
Okay. Well, it's a little more than that, but partially yes. When I come out of the gym, I am sweating a lot. You might notice I sweat through my shirts a lot when I'm teaching. My brow right now is covered with sweat. I sweat. That's what big people do. Some of us more than others. So I am having a lot of vapor going onto my skin. Now, because my body's reasonably warm, it heats up that vapor, I said vapor on my skin, water on my skin, heats up that water and a lot of it leaves. Which molecules are able to leave from my skin? The ones that are hotter than average or the ones that are colder than average? Only the hotter than average ones are able to leave. So I have the hottest water molecules on my skin leaving behind colder ones. Hence, there's a net cooling process because the hottest ones leave, which means that the average kinetic energy is going down my body has to then heat them back up so that it reaches equilibrium with my body, and it's a cooling process. But that's adding more and more water into the atmosphere, and so the amount of water in the car goes up when I get in after working out. Now the windows, outside is the air, which these days is about 40 degrees when I go to the gym. 40 degrees Celsius, that would be very warm. 40 degrees Fahrenheit. So the windows are cold. So the air right next to the windows gets chilled. But that chilled air, I believe this is yours, that chilled air can't hold as much moisture. And so I bring that nice moist air up to the cold windshield. It gets chilled, it can't hold as much moisture, and forms water droplets. That's why my windshield gets fogged up. Okay, now back to the evaporation. If you close a container, you will develop a balance between the vapor leaving and the vapor coming back in. And as you raise the temperature, the amount of moisture that the vapor can hold is bigger, and so you're going to have the balance move around. I want to get to this slide, I think it's this slide, that shows the actual process that we think of for boiling. Nope, the next one. When we think of boiling, I hope it's this one, yeah. When we think of boiling, we think of those those air bubbles coming up, right? That's what you think of as boiling, because that's boiling. Well, why does that occur? It starts with having little air bubbles in the water. And you have air bubbles means that there's an interface between liquid and gas. And you'll have more water molecules then. They're fast enough to break the surface. They can break the surface and go into the air bubble. And that air bubble then, it's going to be the same pressure as everything around it. And you will set up an equilibrium between the air inside and the vapor pressure. As you raise the temperature, the vapor pressure of the water increases because you have more molecules. They're going fast enough to break away. And so you put more and more molecules in that bubble, making the bubble grow bigger, until you get to the point where that bubble then just floats up to the surface, and that's where you have the boiling, because the bubble was growing rapidly. And so those bubbles coming up, that's boiling. What would happen if you had water with no bubbles in it and you heated it up above the boiling temperature? It won't start boiling at 100 degrees Celsius. You need to have those air bubbles to expand and start boiling. That's why in chemistry class, you do something to make sure you don't have catastrophic problems. Nobody wants a student to boil water and have it blow up in their face. And so you put boiling chips into the water. Everybody have experience with that? Most people have experience with that. Some people have experience with that. There are at least a few people that nodded their head. You should always put boiling chips in your water when you're going to boil it, because those boiling chips, you can be sure with the rough edges, they're going to trap some air with them when you put them in. And so you're going to have places that will start boiling. Once you start boiling, it will continue boiling, no problem. But if you have a perfectly smooth surface and you have nice water that's been all purified, has no bubbles remaining, you can overheat it and then have boiling suddenly occur everywhere and a big explosion. I was talking to Ryan earlier about microwaving water. Have you seen YouTube videos about people putting a mug of water into the microwave, pulling it out, and it blows steam everywhere and scalds them? It's because they heated it above the boiling temperature of water, but it didn't have the little air bubbles to start boiling. How can you make sure that doesn't happen? Just don't use a nice new clean mug. If your mug has scratches inside, you can be sure that it's going to have air bubbles trapped in there and it'll never happen. So, I mean, I would say, oh, I got my new mug, let me get out my screwdriver. They're now safe to use. But if you're going to put water in the mug and put it in the microwave, well, of course, just throw a rock. Well, probably don't want to throw a rock in there. But that's the reason that you have all those warnings. And, of course, on Facebook, it's like, it's uncontrollable. There's nothing you can do. Okay, I have to tell you this because it's so disconcerting. A high school classmate of mine posted a question that had this. And it said 92% of people will get this wrong. And I was going to respond, oh, I don't think so. I think most people can do that. But then I looked and there were 2 people who had replied. And they both said the answer was 0. And I was scratching my head. How did they get 0? And so I privately messaged her, said, I didn't want to embarrass these people. I didn't think that you'd have people getting it wrong. And she sent me her explanation, which was also 0. She said, well, 5 times 5 is equal to 25. And then you add the 10. Hopefully everybody now is chuckling. And then you multiply by 0. And then you divide by 5. And clearly it's 0. Yeah, it made me very sad. Everybody understand that this is not 0, right? What's the correct answer? 25. It's 25 because, should be on layer 2, because you do exponents first, then multiplication, division, then addition, subtraction. So this should be 25 plus 0, which is 25. Yeah, it made me sad. I don't know why I thought of that just now. Oh, I mentioned Facebook, and that was a Facebook interaction. Okay, we're going to talk about mechanisms of heating. Here I have a picture of things that might go on in a house. You might have heat coming in a window. You might have heat going up a fireplace. We're going to talk about these. And the first one we're going to talk about is the one here that's called conduction. Conduction occurs when you have 2 objects that make contact with each other. I think you're supposed to light the match first, especially if you can't light matches. Then blow it out. Stay lit. Before it burns my hand. Okay. Plan B is to turn down the gas, but that's no fun. It's more fun to have. Okay, I need some volunteers. Volunteers to come up and show that they are tough. The actual goal is to not let yourself get burned, by the way. I don't want people to... That's
a lot of gas. Okay.
Dang it! I only have 2 matches left.
It's not real fire.
Now I have 1 match left. We might not do this.
Oh my god.
Okay, I'm going to lower the gas because it's still blowing it out.
Do I get money if I get
No, you don't get money. You get fame and fortune.
So I saw it people that are class of things. Oh, good grade. I'll take that. 100%.
Okay. Do I dare turn it up now that it's warmed up? Yeah, I'm going to stop there. Okay, really, I want some volunteers. What we're going to do is we're going to hold this in the flame, and each person will hold on to a piece of metal. And when it gets so hot that you're uncomfortable, let go. Don't say, when someone else is let go, I will let go.
How many do you need?
It has 5 things. Okay.
What's the game here? We burn ourselves?
All right. We got 5 people. Come over on this side, Austin, so you can, not be smashed.
This one's already on the fire.
So
I'll take the long one.
Yeah, I'll hold like this. Okay. So I'm going to put it over there and grab them. Okay. And now, Yeah, grab it. Nothing should be hot now. Now they're just going to hold it until the first person feels uncomfortable and lets go.
It's not centered.
Well, centered. It's up to.
I feel like it's in my game, but I feel like it's hot.
It's up to you guys how it's centered. Now the
I feel like it's going to shock me.
The temperature of the flame is somewhere in the ballpark of 1,200 to 1,500 degrees Celsius. So it's pretty warm flame.
Then you feel like it.
Oh.
No, but it's not uncomfortable.
No.
Yeah, mine's getting there.
Mine's not hot at all.
Mine's not.
Oh.
Mine's not.
Okay, so Michaela let go first. Okay, go ahead. Now if I go through and touch these, I can touch this one that Austin had, no problem. Touch this one here. Yeah, that one, cake. Well, okay, it started to get warm after a while. Not bad. I'm not going to touch the one you had. I know that's the one that gets the hottest.
It got really warm.
Reagan held on too long, and oh my goodness, that was hot, Michaela. Okay. Pete. Yeah, the goal is not to be a masochist, because yeah, that was pretty warm for a few of them. Yeah, it was pretty warm. Okay, so it was different for the different metals. Now, this was conduction. There was direct contact between that center manifold that was hot, actually, because of convection, and the rods people were holding. And the rods were all the same size, but they were made of different materials. So the conduction, the transfer of thermal energy, what do we call the transfer of thermal energy? Heat. The heat depended on the type of material. So let's look at how conduction works. I could demonstrate conduction with this by touching the Bunsen burner, but that would hurt and blister, and I'm not going to do that. So the mechanism for conduction, it's a direct contact mechanism. You have molecules in one thing. In the case of the students here, you have the rod, molecules in the rod are hitting each other. And so the ones that are moving faster, what does that tell you about temperature? Higher temperature, they hit the ones that are moving more slowly, and you have that collision. It makes the ones that are going more slowly go faster. That's the whole process of conduction. So you have to have direct contact. For conduction, we can write an equation for the rate of heating. Heat is energy. Notice here I use slightly different notation than the textbook. I said the power for conduction, I don't think the textbook puts power, but power is the rate at which energy is converted, is Q, the heat, divided by delta T, the time. I don't have a delta with Q because heat is a transfer. Heat is a change in energy. Nothing can actually hold heat. We can't say, oh, that Bunsen burner is hot, therefore it has a lot of heat. We can say it's hot, therefore it could transfer a lot of heat. It could have energy pass away from it, but it doesn't contain heat. So this transfer relationship, we have K, called the thermal conductivity. That is specific to the material. Materials with a higher K are going to have faster transmission of heat through the material. Then we have A. A is the area of the pipe the heat is going through. So in the case of our little experiment with the students, this was the pipe, so A would be the area of the pipe. So you just take that and you say, well, it was going from here to here. The length then is going from here to here. And the area is the area of that circle. So you have the area divided by the length. The way to think about this is the bigger the pipe, the easier it is for the heat to go through. The longer the pipe, the harder it is for it to go through. So that's why the rate is proportional to the area, inversely proportional to the length. Question? It's the cross-sectional area of the thing that it's going through. And then finally, the difference in temperatures. Since it's a difference in temperature, what units should you use? Celsius or Kelvin, because a change in 10 degrees Celsius is the same as a change in 10 degrees Kelvin. So this allows us to calculate conduction. Now let's say that I was going to use this remote control, put one side in the Bunsen burner and hold the other side. If I hold it like this, will I get hotter faster or slower than if I hold it like this? I'm obviously not going to stick it in the flame, but which way would I have more conduction per second? Which way? Okay, like this. Why? Because if I put it like this, my area of the pipe is this area, and the length is only this length. Whereas if I hold it like this, then the area is this area, a smaller area, and the length is longer. So it matters not just what the material is and what its size is, but the orientation for the heat to go through. 4 minutes left. Well, we'll get through these mechanisms of heat. The next mechanism of heat is called, we have to have this first in a clicker question, then we'll go to the next one. These are thermal conductivities for different materials. The ones with high thermal conductivities are the ones that are going to transmit the energy quickly. You notice copper up here is very near the top. So the one that Reagan was holding was copper. So his should have been conducting really fast. If this was made of only metals shown here, I would have to have guessed that Michaela's was silver. I'm pretty sure it's not silver. It's probably an alloy of something that has a high thermal conductivity, because clearly hers got hot fast. Which ones got hot slowly? Well, if we look here, if we look at the metals, we'd see stainless steel has by far the lowest thermal conductivity. So if you happen to grab the one that was stainless steel, you could be holding it for a long time before it gets hot, because it doesn't conduct very readily. Where is air on this list? It's at the very bottom. Air is a very bad conductor of heat, or a very good insulator. So I see like Michaela's wearing a sweatshirt. What's the goal of the sweatshirt? To trap air. The air is what's acting as the insulator. And the purpose of the sweatshirt is to trap it so you have an air droplet here, or air, I guess we don't call them droplets, but a bubble of air or something like that. But the air can't move from one place to another. It gets trapped there and provides really good insulation. Notice that ice is reasonably low, so ice makes a reasonably good insulator. Hence you make an igloo. The igloo is made out of ice, which is cold. But heat can't go very quickly through that ice. And if you make that igloo so it has a fairly thick wall, it's going to take much longer for heat to get through, and you can raise the temperature inside to a nice comfortable, let's say 55 degrees Fahrenheit, while the temperature outside is a very uncomfortable minus 40 degrees Fahrenheit. And you have the ice acting as your insulator. Okay, now a clicker question. Which material is the best insulator? Copper, iron, air, or wood? I like the authority there, Reagan. You got that answer in there. Okay. We had given time, we won't discuss this. Air was the best insulator in the table. Copper was the next to worst insulator. Copper would be a horrible insulator because heat goes through it real easily. Wood's a reasonably good insulator. Okay, the next mechanism, convection. If I take my hand and I put it up here, it gets warm really quick. Why is it getting warm?
Hot air rises.
Because hot air rises. That is the essence of convection. Convection is the heat is being transported by a fluid, usually a fluid that's driven by the temperature difference. So the hot air rises, it heats me up. This here is an example of a gravity furnace. You heat the air goes up. Of course, because the air went up, it pushed cooler air down. The cooler air comes into the furnace, gets heated up, and you create a cycle of air, which we call a convection cycle. These convection cycles are what drive our weather patterns on Earth. The final of our heating mechanism, this is just why fur is good. I'm not going to go over that. The final one is radiation. Even if I hold my hand over here, it gets warm. It's getting warm because there's electromagnetic waves coming from that. And those are carrying energy. That's heat. And the equation for radiation is proportional to the temperature raised to the 4th power. So hot things radiate a lot more than cold things. Right? You double the temperature, it's 16 times more radiation. Other things in this equation, that is just a constant. It's called the Stefan-Boltzmann constant. This thing is a Greek letter epsilon. Our textbook just uses E. That's called the emissivity. It's a measurement of how efficient something radiates energy. Black things radiate really well. They also absorb really well. White things or silver things radiate really poorly and absorb really poorly. A is the surface area, and of course T is temperature. We're out of time, so I will stop right there. I was going to do a problem. We won't do that problem.